These are your 7-2B notes on writing equations of exponential functions. So we are going to work through ordered pairs and come up with the equation that goes through those two ordered pairs. We did this with linear functions, quadratic functions, all the way throughout the year. So it's a little bit different. They're going to give us two ordered pairs. One of the ordered pairs that they give us is going to be 0, comma, the a value. Remember, the a value is the y-intercept, and the y-intercept is when x is 0. So since they give us the y-intercept, this value, this number, has to go in the place of the a value in the equation. Then the other ordered pair that they give you is an x and a y value. So you're going to plug that in for the exponent x and for the y value. And then the only number remaining is b for the base. So you're going to solve for the base. And then once you get the base, you're going to plug everything in and write it as an equation. So this first example, 0, -5, that means this is the a value. And then the x value and the y value are the other ordered pair. So every time, we're going to start off and we're going to write it the exponential form first. So you have it and you use it as a formula. The y value is -135. The a value is -5. We don't have the b value. And my x value is -3. So whenever you have a -3, we'll have to make that positive before we can solve for b. So now using inverse operations, I'm going to take care of the -5 first to get b by itself. So I'm going to divide 135 by 5, or negative. We end up with 27, and it's positive because it was a negative divided by a negative. And so this gives me a base to the -3rd power. Now what we want to do is we want to make that a positive 3. So if I flip the one side, that will allow me to flip that to a positive 3. So if I take the inverse of 1/27th, that will make this a positive 3. You actually want to flip the number and not the b value. Otherwise, you'll have like a 1 over b, and that gets annoying. So flip, take the reciprocal of the number, and that allows us to say that now we have a positive 3 value. Take the cube root of both sides to undo the cube. And when you take a cube root of a fraction, you're actually taking the cube root of the numerator over the cube root of the denominator. The cube root of b cubed is just b. Cube root of 1 is 1, and the cube root of 27 is 3. So this ends up being a base that's 1/3. This would be a decay equation because it's less than 1. And so we end up with, in the end, I can just write that down as y equals -5 times 1/3 to the x power. And so keep the -5 separate from the 1/3 because the 1/3 is what we're raising to the x power. So this is our answer. So our answers are going to look like equations. This is the function that if I were to graph it, it would go through 0, -5, and -3, -135. Let's try another one. They give us 0, a value. That's my y-intercept. And then they give me an x and a y. So y equals a times b to the x. 54 equals 2 times b to the 3rd. Divide both sides by 2 first. I get 27 is equal to b to the 3rd. Cube root both sides. The cube root of 27 is 3. So the base is 3. This is a growth equation because it's greater than 1. And so y equals 2 times 3 to the x power. This is the equation that when you graph it will go through 0, 2, and 354. If you wanted to check it, you could plug in 0 for x and you should get 2 for y, which it does. And if you plugged in 3 for x, you should get 54 when you solve it. So you can always check this by plugging in the points to solve. Word problem. Kristen starts an experiment with 7,500 bacteria cells. Okay, if you start the experiment, that means after 0 time, after 0 hours. So we have 0 hours, 7,500 bacteria cells. There's an ordered pair. After 4 hours, there's your time. After 4 hours, there are 23,000 bacteria cells. Write an exponential function that could be used to model the number of bacteria after X hours. Well, you can clearly see as time increases, the amount of bacteria increased. So my base better represent growth. It better be a number greater than 1. So when I use the formula, y is equal to a times b to the x. 23,000 is equal to 77,500 times b to the 4th. I'm going to divide by 7,500. And I'm running out of room here, so I'm just going to bring it over here. And when you divide the 23,000 by 7,500, you end up with 3.06 repeating. Just leave it on your calculator is equal to b to the 4th. And then we're going to take the 4th root of both. And when you take the 4th root of that, give me 1 second. We end up with 1.323, or just 32. It's not a really big number, but it wasn't a great big growth. And so it is greater than 1, which represents growth. And so my base is 1.32. So the equation would be y equals 7,500 times b, not times b, times 1.32 to the x power. Again, you can plug in the ordered pairs and see if you get the right answer. The extension to that, how many bacteria can be expected after 12 hours? Well, since 12 represents the actual x value, if I use this equation now, I can find the y value given 12 as my x value. So I'm going to use y equals 7,500 times 1.32 to the 12th power. Order of operations says I need to take that to the 12th power first. I'm going to leave it in my calculator and then times it by 7,500, and you end up with 216,302 bacteria. It went up pretty big. It looks like a reasonable answer after 12 hours. So your lesson summary, I need you guys to give me an example of a base value that would represent growth, and then give me one that would represent decay. And then I want you to write the equation, the exponential equation of the equation that goes through those 2 points. Good luck.